All right, folks, Chapter 5 is all about the derivative and applications of the derivative. Here in Section 5.1, we're going to look at first derivatives and what it tells us about the graphs of functions. So our section objectives in Section 5.1 will be Objective 1, analyze the relationship between the sign of f prime and the behavior of f. So whether or not the derivative, when we say sign of f prime, we're talking about if the derivative is positive or negative. Objective 2, we're going to determine these things called critical values. In Objective 3, we're going to learn and start to use and apply the first derivative test. And number 4, we'll look at a specific application using the first derivative test. So we're going to introduce this material so you can see where this stuff comes from through an example. So here are two functions. F of x equals 1/3 x cubed plus 2x squared. And the derivative of that function is x squared plus 4x. Here's what their graphs look like. And here's what we are going to determine based on the graphs of these of the function and the function's derivative. In part A, we're going to analyze where the function is increasing, part B, where the function is decreasing, and then in part C, where the function is constant. In part D, we're going to determine where the derivative is positive, in part E, where the derivative is negative, and in part F, where the derivative is equal to 0. So there's much to do here. So I'll hopefully get this written down. The example, the functions, make a quick sketch of the graphs, get this in your notes. Because I'm going to head off to the board and we're going to analyze each part at the board and see what our analysis suggests. All right, folks, here were the graphs that we just saw on the slide and parts A through F that were asked. So part A, here's the graph of the function, 1/3 x cubed plus 2x squared. We're asked where is the function increasing. So, when you are asked to find where a function is increasing, we're talking about values of x. We're talking about an open interval where the function's increasing. So when you read the graph from left to right, where is it going up? That's where it would be increasing. And it looks like it's increasing from negative infinity to an x value of -4. And it looks like it's increasing from an x value of 0, to infinity. So it's increasing on the interval negative infinity to -4, union with 0 to infinity. So part B, where is it decreasing? Well, as you read from left to right, decreasing would match up with where is it going down. And it looks like it is decreasing from an x value of -4 to an x value of 0. So it's decreasing on the interval -4 to 0. Notice these are open intervals. Then where is the function constant? Well, it will be constant at the values of x where it is neither increasing nor decreasing. And that appears for this function that we have that occurring right here at the x value of -4 and right here at the x value of 0. So the function is constant at x equals -4 and at x equals 0. So let's come over here and let's answer the questions, parts D, E, and F, for the derivative. Here's the graph of the derivative of that function. Part D, where is the derivative greater than 0? Well, graphically something is greater than 0 where the graph is above the x-axis. So it looks to me like the graph of the derivative is above the x-axis from x values of negative infinity to -4 and x values of 0 to infinity. So the intervals would be -infinity to -4 union with 0 to infinity. Where is the derivative less than 0? Well, graphically that matches up with where is the graph of the derivative below the x-axis. And it looks like the graph of the derivative is below the x-axis for x values from -4 to 0. So that interval would be -4 to 0. And then finally, where is the derivative equal to 0? Well, it's equal to 0 at the x-intercepts. So it looks like the derivative is equal to 0 at -4 and at 0. So the derivative is equal to 0 at x equals -4 and x equals 0. So now check it out, folks. Where the function is increasing, the interval where the function is increasing matches up exactly with the intervals where the derivative is positive. And I tried to color code it on the graphs as well. The function is decreasing. It matches up exactly with the same interval as where the derivative is negative. I tried to color code that. And the function is constant at the values of x where the derivative is equal to 0. This is an important relationship between the derivative and how it tells us the behavior of a function. In short, where the derivative is positive, the function's increasing. Where the derivative is negative, the function is decreasing. And where the derivative is 0, the function is constant. So let's head on back to the slides and kind of formalize this just a little bit. All right, folks, that example that we just looked at suggests the following, that if you have an open interval AB where the function is differentiable and continuous, that if the derivative, number one, if the derivative is greater than 0, it's a positive, for all x in AB, then the function is increasing on the interval AB. If the derivative is less than 0, then the function is decreasing. And if the derivative is equal to 0, then the function is constant. Let's look at one quick figure of this. The blue graph is the graph of some function. So you can see where the function is increasing, where it's decreasing, and the sign of the derivative. It's positive. The derivative is positive. Function is increasing. The derivative is negative. The function is decreasing. And where the derivative is 0, the function is momentarily leveled off, or we say it is constant. So if f is a continuous function on an open interval containing c, then the point CF of c, well, that point is called a relative maximum if f of c is greater than or equal to f of x for all x in the interval. So think relative maximum, it's kind of like the top of a hill. You're at a relative maximum. So if, the point CF of c is the highest point, you're at a maximum. The point CF of c is called a relative minimum if f of c is less than or equal to f of x for all x in the interval. So here you're kind of like at the bottom of a valley. A little vocabulary. Collectively, maxima, that's plural of maximum. Minima is plural of minimum. They're collectively called relative extrema. So let's check out this graph that's going to pop up here in a second to the right. We're going to look at the graph and determine where the graph has a relative maximum and where it has a relative minimum. And while we're here, we'll also determine intervals where the function is increasing and decreasing. So here's the graph of the function. I don't know what the function is. More importantly, I don't care. But get this example in your notes, reproduce the graph, because I'm going to head off to the chalkboard and do this one. All right, folks, we were given this graph of some function. Don't know what the function is, don't care. And we're asked to find where there would be a relative maximum, a relative minimum, and also determine intervals of increase and decrease. So, one thing I'm gonna do over here, I'm gonna kind of foreshadow what's coming up here real soon, is let me just make a number line right here, and on the number line, let me put -4, -2, and 2, and let me just put f. I'm gonna symbolize the behavior of the function. So from -infinity to -4, the function is decreasing. So let me use that symbol to communicate. It's like shorthand notation saying it's decreasing. From -4 to 2, the function is increasing. From -2 to 2, the function is decreasing. And then from 2 to infinity, the function is increasing. Well, it looks like I've answered part of the questions here. Determine intervals of increase and decrease. So I could say the function is, and I'm going to use that symbol to represent increasing. The function is increasing on the interval -4 to -2, union with 2 to infinity. The function is decreasing. Let's see, it's decreasing on the interval -infinity to -4, union with -2 to 2. And also, it looks like, just look at this right here. If my function is decreasing and then it starts to increase, I've hit a bottom here. I've hit like the bottom of a valley. I've hit a relative min. Graphically, I can see that's a low point. For all points close by, that's the lowest point. So let me write that down. There's a relative min at x equals -4. Likewise, if my function is increasing and then it starts to decrease, I've hit a high point at this x value. I've hit a relative max. Let me write that down. There's a relative max at x equals -2. And then continuing, if my function is decreasing and then starts increasing again, I've hit a valley bottom, as we can graphically see right here. So that's a relative min. So let me just toss that in right here. And, well, that's it, folks. I think we've answered all the questions, for this example. Now, technically speaking, the relative maximum, relative minimum, technically speaking, it's the y coordinates. We'll end up listing them as ordered pairs, but I just wanted to tell you about the technicality. And so our next task is, we're going to go back to the slides to see, how is it we're going to use, how is it we can find these relative max and relative mins when we don't have a graph, but we're given a function. So let's head back to the slides and see what is next. All right, now that example that we just looked at and the exercise that we briefly looked at as well should be getting you dialed into the concept of a maximum and a minimum. But we're going to head back to the board and we're going to look at the graph of some unknown function. So I'm going to go to the board. I'm going to put a graph on the board. You want to put it in your notes. And we're just going to make some observations that will help us going forward. So back to the chalkboard I go. All right, here we are back at the board pretty quickly. Folks, here's the graph of some function. I don't know what the function is. I don't care. Let's just answer these questions, one more time. Relative max, relative min. So for this function, for what values of x do we have a relative max? Where do we see like a high point, a local high point? Well, it looks like this is a relative max. So let me list that at x equals a. It looks like at b, that's not a relative max. That's like a valley bottom. So that's a relative min. Let me list that right here. We have a relative min at x equals b. So at x equals c, well, we've hit another high point, so that's a relative max. And when we get to the x value of d, we've hit like another, local low point, so that would be another relative min. All right, so now it's time to ask a calculus question. We don't know what the function is, so we can't get the derivative of the function, but we should be able to determine if we could find the derivative and evaluate it at a, what number would come out? Would it be a positive number? Would it be a negative number? Or would it be 0? Well, remember, derivative tells you the slope of a tangent line. So here's x equals a. If I draw a tangent line at that point, it'll look something like this. The tangent line is horizontal. Remember, horizontal lines have 0 slope. So even though I can't find the derivative, I don't know what it is, I know f prime of a must be 0. Likewise, at b, I'd have a horizontal tangent line. So f prime of b is also 0. Now what about f prime of c and f prime of d? What's f prime of c and f prime of d? Nah, it's not 0. Remember back in chapter 2 when we first learned the derivative, something that we talked about at that time was when the derivative doesn't exist. Remember, graphically, the derivative does not exist wherever the graph has one situation where it has a sharp turn or a corner. It looks to me like the graph is making a sharp turn at x equals c. And it looks like it's making a sharp turn at x equals d. So for both of these, the derivative is undefined. Folks, that's the only way you can have a relative max or a relative min, those cases over there. You can only have a relative max or a relative min at values where the derivative is 0 or at values where the derivative is undefined. Those are the only situations where you can have a relative max or a relative min. And because this is so critical to our study of what's going to happen here in this section and in chapter 5, let's head on back to the slides and let's formally write this down as a definition. All right, folks, based on our analysis of the graph we just looked at on the board, it appears that values in the domain of a function where the derivative is 0 or where the derivative is undefined, it's critical in our analysis. This gives rise to the following definition. It's an important definition. It's the definition of a critical value. We're going to say a critical value for a function f is an x value in the domain of the function for which the derivative is 0 or the derivative is undefined. So please, make special note of this. A critical value is where the derivative is 0 or where the derivative is undefined. So this is going to be critical for our work here in Chapter 5. So our first attack here right now is to just determine critical values for some functions. So, well, you know the drill. Write the example down, parts A and B, because I am going to head off to the chalkboard and work through these examples. All right, we just saw the definition for a critical value. One more time, a critical value. We call something a critical value for a function if it's an x value that's in the domain, so you have to be in the domain of the function, where the derivative is 0 or the derivative is undefined. So in this example, we're asked to simply find the critical values. So find the critical values for the function 2x cubed plus 3x squared minus 36x plus 14. So in general, critical values occur where the derivative is 0 or the derivative is undefined. So the first thing we should do is find the derivative. So the derivative is 6x squared plus 6x minus 36. Okay, now we need to determine where does the derivative equal 0 or where is the derivative undefined. Let's quickly do the undefined case first. The derivative is a quadratic. It's a polynomial function. We know it's defined everywhere. So there are no values of x where the derivative is undefined. Next, then let's see where the derivative is equal to 0. So we take the derivative, set it equal to 0, and we have a friendly little quadratic equation to solve. I would start off by factoring out the 6. And then I will try to factor this trinomial. I hope it factors. If it doesn't factor, I'm going to have to use the quadratic formula. So let's see. X squared means there'd be an x here and an x here. Factors of 6, I'm thinking 3 and 2. I believe it's a plus minus. And I should check it real quick. X times x is x squared. 3 times negative 2 is negative 6. There's negative 2x plus 3x would give me a positive x. So it does check. And then we know we set each factor equal to 0. And we then determine that the critical values for this function are negative 3 and 2. That's not too bad. Part B, the function is f of x equals the cube root of x plus 1. Trying to find critical values. That means we're trying to find where the derivative is 0 or where the derivative is undefined. So the first thing I should do is get the derivative. So, I'm going to rewrite this as x plus 1 to the 1/3 so I can get the derivative to be 1/3 times x plus 1 to the negative 2/3. And then I remember the chain rule, times the derivative of the inside. Well, the derivative of the inside is 1, so it's times 1. And I've reached a point where, I'm going to have to simplify this derivative. It's not too bad. We just drop the x plus 1 to the denominator to make the exponent positive. All right. So, my derivative is 1 over 3 times the quantity x plus 1 to the 2/3 power. I need to determine where this derivative is equal to 0 or where this derivative is undefined. Those are because I'm finding critical values. So let me just kind of make the following comment. My derivative looks like a fraction. I don't care what fraction you think of. So let me just generically say I'm thinking of the fraction a over b. It doesn't matter what the numerator is and the denominator is. I'm talking about something in a big in general statement here. For any fraction you can think of, So for any fraction you can think of, a over b, for a over b to equal 0, the numerator has to be 0. For any fraction a over b to be undefined, the denominator must be 0. So now let's look at the derivative. It looks like a fraction. The only time this derivative will be equal to 0 is when the numerator is equal to 0. Are there any values of x that will make the numerator equal to 0? No. 1 is taking up a permanent residency in the numerator. The numerator is always 1. There is no value of x that's going to make the numerator 0. So that means the derivative is equal to 0, well, nowhere. Undefined. Is the derivative undefined anywhere? Well, it would be undefined if there's a value of x that makes the denominator 0. That's why I did this real quick. So look at the denominator. Is there a value of x that would make the denominator 0? I think -1 would, because -1 plus 1 is 0, 0 to the 2/3 is 0, 3 times 0 is 0. So the derivative is undefined at x equals -1. And that is the only critical value for that function. Okay, it's really important that you can find critical values. You know, I think earlier I said that was going to be critical to what we're doing in this chapter. Well, they're called critical values. That's how critical locating these values are. So I want you now to go to section 5.1 exercises. I want you to pause the video. I want you to do number 24. After you do number 24, restart the video. I'll be here at the board working through the solution, and hopefully you will have found the critical values. All right, folks, at number 24, you were asked to find the critical values for the function f of x equals -x cubed minus 3x squared plus 45x minus 5. Remember, critical values occur where the derivative equals 0 or where the derivative is undefined. So the first thing we need to do, get the derivative. So the derivative is a -3x squared minus 6x plus 45. So let's do the undefined case first. This derivative is undefined nowhere. It's defined for all values of x. It's a quadratic function. It's a polynomial function. Polynomials are defined everywhere. So the only critical values will occur where the derivative is equal to 0. And in trying to solve this little quadratic, I would probably begin by factoring out a -3, taking out a greatest common factor. And so I'd have -3 times the quantity x squared plus 2x minus 15. And then I try to factor this trinomial. If it doesn't factor, I have to use the quadratic formula. Let's see, x and x. I think of factors of 15. What pops into my head are 5 and 3. So 5 and 3. I think this is a plus and that's a minus. A quick check. X times x is x squared. 5 times -3 is -15. That would give me a -3x plus a 5x is a 2x, so it checks. I take the factors, set them equal to 0, and I determine that the critical values are -5 and 3. So hopefully you were able to get those critical values. All right, let's head back to the slides and see what we can do with these critical values. All right, now that we've looked at practicing, finding critical values, let's continue on and see what we can do with the critical values. First, I want to make a quick note. Not every every relative extrema, that means every relative maximum or relative minimum, occurs at a critical value. But not every critical value produces a relative extrema. So if you have a critical value, it doesn't mean it's going to produce a relative max or a relative min, but a relative max or relative min can only occur at a critical value. And the way we can determine if a critical value is yielding a relative max or a relative min is through the first derivative test. So here's your first derivative test. X equals c is a critical value of a function f. The function's continuous on an open interval that contains x equals c. The point c f of c, it can be called a relative maximum if f prime of x is greater than 0, the derivative is positive, to the left of c, and f prime of x is less than 0, the derivative is negative, to the right of c. And probably the best way to remember this is through a simple sign diagram. So let me show you what it would look like for those words. We're going to start making sign diagrams. Notice, we have a real number line here. I've located c, the critical value, on the number line. We'll determine the sign of the derivative, if it's positive or negative, and that tells us if the function is increasing or decreasing. And just by looking at the sign diagram and the arrows showing where the function is increasing and decreasing, it visually tells you that if you're increasing, you're going up, and then you hit x equals c and you start to decrease, you're heading down, that you've obviously hit a high point, a relative maximum. Similarly, a relative minimum, you have a relative minimum if the derivative is less than 0, negative, to the left of c, and the derivative is greater than 0, it's positive, to the right of c. So the sign diagram for that, it would look like this. And I think it's visually apparent when we can determine where the function's decreasing and increasing. We'll know if we have a maximum or a minimum. So let's practice this a little bit. So here's an example. Write this example in your notes. For this function, we're going to determine intervals where the function is increasing and where the function is decreasing. And I will show you how to make a sign diagram to aid in our work here. It's a nice visual way to summarize everything. And once we have the sign diagram made, we'll then locate all relative extrema. So get this written in your notes because I'm heading off to the chalkboard to work on it. Hey folks, in this example we were given the function 2x cubed plus 3x squared minus 36x plus 14. We were asked to determine intervals where the function is increasing and where the function is decreasing. And also we were asked to locate all relative extrema. So here's the paradigm. This is the process you would go through. I'll write it over here. First thing you need to do, get the critical values. The second thing you do, make a sign diagram. That will answer all of the questions. It will tell us where the function's increasing, where the function's decreasing, where we have relative max, where we have a relative min. So remember, critical values occur where the derivative equals 0 or where the derivative is undefined. So I guess we should find the derivative first. Now I think in the prior example, we did determine the critical numbers or the critical values for this function. I think we ended up saying that the critical values were x equals -3 and x equals 2. So now we'll make a sign diagram. So here's how I make a sign diagram. First thing I do, I make a number line. On the number line, I put all of the critical values that I found. So on my number line, I would put -3 and 2. And then I do the following bit of bookkeeping to keep my work organized. And about this position here, I put F prime, and here I put F. Now remember, it's the sign of the derivative that tells us the behavior of the function. If the derivative is negative, we know the function's decreasing. If the derivative is positive, we know the function is increasing. So on the interval, -∞ to -3, I need to determine if the derivative is positive or negative. And here's the quickest, easiest way to do that. Pick a value of x. Pick anything that you know is definitely in the interval -∞ to -3. I mean, I would pick -4. Evaluate the derivative at -4 to see what comes out, a positive number or a negative number. I don't care what the number is, I just need to know if it's positive or negative. So evaluate the derivative at -4. All right, now I'm going to kind of do this without a calculator because I have the factored form of the derivative here. So I can think about putting -4 in for the x's. If I put -4 in here for this x, well, -4 plus 3 is -1. The key word is negative. So when -4 comes in for x, this factor is negative. When -4 comes in here for x, this factor is also negative. So when -4 comes in for x, I would have a positive times a negative times a negative. Positive times negative times negative. That is positive. So on the interval -∞ to -3, the derivative is positive. That tells me the function is increasing. Now I move to the next interval, which is -3 to 2. And I go through the same process. Pick a number that you know is definitely in the interval -3 to 2. I mean, personally here, I would pick 0. Evaluate the derivative at 0 to see what comes out. So 0 comes in for the x's, into the derivative. And let's see, this factor would be positive, this factor would be negative. Positive times negative, that is negative. So on the interval -3 to 2, the function is decreasing. Then finally on the interval 2 to infinity, pick any number that you know is in the interval. I mean, hell, if you want, you could pick pi. Pi's in that interval. I wouldn't. I would pick x equals 3. Put 3 in for the derivative. You want to see what comes out, positive or negative. So 3 comes in here for the derivative. This factor would be positive. This factor would be positive. A positive times a positive times a positive. Yep, it is positive. Folks, the sign diagram answers all of the questions. The sign diagram tells me the function is increasing. Well, it's increasing on the interval -∞ to -3, union with 2 to infinity. The function is decreasing on the interval -3 to 2. It also tells me that we have a relative max. I can see increasing, decreasing. Here's a relative max. I've hit a high point. So it tells me that we have a relative max at x equals -3 and a relative min at x equals 2 because I'm decreasing and then increasing, so I've hit like a valley bottom. Now what I'm going to do is I'm going to list the relative max and the relative min. I'm going to list it as an ordered pair. So I know the relative max occurs at x equals -3. That would be the point -3, comma. Now we're talking about an actual point that's on the graph of the function. So to get the y-coordinate, I have to evaluate the function at -3. I have to put -3 back in for the x's. And I used my calculator to do that. And I got a y value of 95. So the relative max is at the point -3, 95. Likewise, the relative min, I need to get its y-coordinate. So I take this value of x, toss it back into the function, and I ended up getting a -30. So the sign diagram does it all for us. So to recap, when asked to find intervals of increase and decrease for a function as well as relative extrema, you want to find the critical values and use that to make a sign diagram. The sign diagram answers everything. So to make sure you're kind of dialed in with this, in section 5.1 exercises, I would now like you to do number 38. The nice thing about 38 is it already uses the work that you did in exercise 24. So it'll save you a little bit of time. But pause the video, do number 38. Once you finish 38, restart the video, and hopefully you'll see that you got the answer correct. All right, folks, in number 38, you're asked to find intervals of increase and decrease and the relative extrema for this function. That was the function that you looked at in exercise 24. So I just wrote down what we had as the final derivative and what the critical values were. We already did part of the work. So now it's make a sign diagram. Put the critical values on the sign diagram. I put f prime here, I put f here. And remember, you pick any number you want in this interval. I would pick -6. You're tossing that into the derivative to see if a positive or negative comes out. So -6 comes in here for the derivative. We would have a negative. This factor would be negative. This factor would be negative. So a negative times a negative times a negative, that is negative. The function is decreasing. Alright, I come to this interval, -5 to 3. I can pick any number I want. I would pick 0. Remember, I'm going to toss that number 0 into the derivative to see what comes out, positive or negative. So I put 0 in for x. This factor's positive. This factor would be negative. A negative times a positive times a negative. Well, negative times positive times negative, that's positive. So the function is increasing. Finally, out here, you can pick any value you want that's in the interval 3 to infinity. Did anyone pick pi? Yeah, I wouldn't. I'd pick 4. And when 4 comes into the derivative for the x, this factor's positive, this factor's positive. So a negative times a positive times a positive, that's negative. The function is decreasing. So the sign diagram tells us that the function is increasing on the interval -5 to 3. The function is decreasing on the interval -infinity to -5, union with the interval 3 to infinity. And more to it, it tells us the relative extrema. Decrease, increase, that's a relative min. Increase, decrease, that's a relative max. So we have a relative min at x equals -5. We have a relative max at x equals 3. And again, I like to list them as ordered pairs because we're talking about points that are actually on the graph of the function. So when I evaluate the function at -5, to get the y value, I get the relative min is at the point -5, -180, whereas the relative max is at the point 376. So hopefully you got that and you see this isn't too bad at all. But let's head back to the slides and see what we have coming up next. All right, so hopefully we're starting to get dialed in. We understand how the derivative tells us where a function is increasing or decreasing, how the sign diagram and summarizing that information can also tell us where we have a relative max or a relative min. The sign diagram is a wonderful visual way to represent the first derivative test. So what we have left in this section is to do an application. So again, get this written down. I know there's a lot of words. I'm going to go to the board and I'm going to work through it. But for this function, we are going to, it's a function that is modeling concentration of medication. For this function, what we're going to do in part A, we're going to find the critical values. Then that will help us find intervals where this function p is increasing and decreasing. And then we're going to find the relative maximum and interpret each coordinate of the relative maximum. So again, get this written into your notes because I'm heading off to the chalkboard. All right, folks, this example, a lot of words, should have written it all down, should have it in your notes. I just wrote down what the function is. It's representing concentration of medication during the first 20 hours after the medication was administered. T is time in hours, and P of T is the concentration of the medication as a percentage. In part A, we're asked to determine the critical values and the intervals where the function P is increasing and where it's decreasing. And then in part B, determine the relative maximum and interpret each point. So for part A, critical values, we need the derivative. We need to get the derivative. See where the derivative is 0 and where the derivative is undefined. So to get the derivative here, let's see, that's going to require the quotient rule. So the quotient rule, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and then all of that stuff over the denominator squared. Okay, I do have to simplify this. I have a lot of work to do here simplifying. So the first thing I would do, I'm going to tell you what I would do each step, and I'm just going to write down the simplified version. I would distribute this 230, and here I would distribute the negative 230. Then I would combine the like terms in the numerator, and I end up with the numerator simplifying down to negative 230 t squared plus 2070. And, well, the denominator, I'll leave it like that. All right, so here it is. We have derivative. Looks like a fraction. So remember, the only time a fraction is equal to 0 is when the numerator is 0. The only time a fraction is undefined is when the denominator is equal to 0. So I'm going to do the undefined case first. The denominator is undefined when t is equal to 3. I'm sorry, when t is equal to negative 3. But that value of t, negative 3, we don't care about for a couple of reasons. One, it's not in the interval 0 to 20. And two, since t represents time, a value of negative 3, I mean, what does that mean? We're time traveling? So, more importantly, the value of t that makes the denominator 0 is negative 3, And since negative 3 is not in this interval, 0 to 20, it's not part of our restricted domain, we don't care about it. So now where's the derivative equal to 0? Well, where does the numerator equal 0? Well, if I add the 230t squared to both sides of the equation, divide both sides by 230, and then take the square root of both sides, I get t is plus or minus 3. But both of those are not critical values for this function because, again, the negative 3 is not in the interval 0 to 20. So this function only has one meaningful critical value in this problem context. T equals 3 is the only meaningful critical value. So the only critical value that's meaningful here is t equals 3. So like we always do, we make a number line. Put the critical value on the number line. But also on this number line, I'm going to put two more numbers. I'm going to put 0 and 20. Because we don't care what is happening for values of t that are larger than 20. I mean, look at this. We don't care what's happening for values of t that are less than 0. We only care on the interval 0 to 20. And let me finish off my notation. P prime and P. So it's the same process, folks. Pick a number in the interval 0 to 3. Pick a friendly number, like 1. Pick 1. You're tossing that back into the derivative to see what comes out, positive or negative. Well, look at this. No matter what you put in for t, for t equals 1, the denominator's positive because it's squared. The numerator, when 1 comes in for t, well, this would end up being negative 230. Negative 230 plus 2070, that's positive. So when 1 comes into the derivative for t, we'd have a positive divided by a positive, which is positive. The function is increasing. Then we pick a value for t in the interval 3 to 20. I would probably pick 4. So I toss 4 into the derivative. The denominator's positive. Negative 230 times 4 squared, that's negative 230 times 16. I don't know what that is, but I know it's a negative number that's larger than 2070. So when 4 comes in for t, the numerator's negative, the denominator's positive. Negative divided by a positive is negative. So the function's decreasing. So let's answer the question. The function p is increasing on the interval 0 to 3. It's decreasing on the interval 3 to 20. Which means in part B, there is a relative max at t equals 3. Then I need to get the y coordinate for that value of t. So I evaluate the function at t equals 3, and I'm going to round this to 2 decimal places. I get a 19.17. So the interpreting what each one of these coordinates tells us. So here's what it says. 3 hours, that's where the 3 is, after the administration of this experimental drug. So 3 hours after administration of this experimental drug, the concentration is maximized at 19.17%. And that's all there is to this one. So that's it for section 5.1. So at this time, you're good to go. So head off, do all the exercises in section 5.1. Thanks for watching.